Good morning, student doctors. This is Mr. B, and today we'll be starting our first physics lecture. Um, this physics lecture is going to be primarily for the chemical and physical foundations of biological systems section of the MCAT. So remember, physics and chemistry are going to be the foundations for this section, and today's topics are going to be the metric system. And of the metric system, we're going to talk about the 7 SI units. And we're also going to be talking about translational motion. Alright, guys, so let's first talk about the metric system. Alright, so the metric system is also called the International System of Units. International System of Units. And of this, okay, so we have 7 SI units that we definitely need to know for the MCAT. Okay, so 7 SI units. All right, and these 7 SI units include 1, length, right? And the way length is measured in the metric system is in meters m. All right, and then the second SI unit that we need to know is time, and time is measured in seconds. Seconds S, denoted S. 3 is the amount of a substance. Amount of a substance will be denoted in moles, little m, right? And electric current, right? The current that goes through a wire will be measured through amperes. And we have a few other ones, right? So amperes is A. And 5 is temperature, which is in kelvins. All right, kelvins in K. And mass is in kilograms. Right, kilograms, kg. And we also have another one. You're not going to see it as often, but it's called it's called luminous intensity. And that's measured in CD. Candelas. Alright, so why will we need to know length? Okay, so they're going to give us a lot of questions where units of length, right, like displacement, values of x will be measured in kilometers, meters, millimeters, and they're going to ask for you to convert from one to the other, right? Primarily, you're going to have to convert into meters. And then you're going to have time in terms of seconds, where you're going to have to convert, I don't know, sometimes from hours to minutes to seconds, right? And then, moles, right? We have to go from Avogadro's number to the amount of moles. And then, electric current will probably be given to you, but they might give it in the form of, milliamps or KAs, right? We also will need to know. So we will also need to know temperature in where we have to convert it from Celsius to Kelvins, right? We had to add 273 degrees, right? And mass to kilograms. Mass to kilograms, a lot of conversions here. This is probably going to be one of the more important ones. The type of conversions that we're going to do. First, let me erase some of this. Actually, let me just erase this right here. So mass to kilograms, right? We're going to have to convert from mass or grams to kilograms. We're going to have to go from milligrams to grams. We might have to go from centigrams to grams, right? So we're going to have a lot of these different conversions that we need to do, okay? But the most important ones, right, that we need to know are length. We need to know how to convert from meters to kilometers, kilometers to meters, meters back to millimeters, millimeters back to meters, and we need to know how to go back and forth. All right. So that's one of the measures that we need to know. Conversions between meters, right? We need to know conversion in terms of seconds. We need to go from hours to minutes to seconds, seconds to minutes to hours, right? We also need to be able to convert from moles to particles using Avogadro's number, which we will do in chemistry, right? Right, so we're just going to erase that. And we're also going to need to be able to use those same conversions, right? Knowing the different prefixes, we need to be able to know how to convert from milliamps to amps, or milligrams to grams, or millimeters to meters, right? And so forth. And we're going to show you how to do that in the next slide. But just want to show you these basic SI units that you're definitely going to see on your MCAT, all right? Just so that you have a better understanding of what you need to know. Temperature to Kelvin, right? We use kelvins because it's absolute. It's an absolute value versus Celsius, which is a relative value, right? And we'll talk about that when we get into chemistry. And then we go from mass to kilograms, right? But we go from kilograms to grams, right? Because most things are measured in grams in chemistry, right? Or in just science overall. So these are all the areas that you're going to see on your MCAT. All right, so I just kind of want to show you the power of the metric system. This kind of helped me understand it when I was first learning for the MCAT. So let's look at meters. Let's look at meters. And the degree of its power in terms of the universe, right? In terms of the universe to the nucleus of an atom. All right? All right. So let's just look at our universe, right? So in our universe we have multiple galaxies, right? All right, and then here we have what we call, our galaxy, Milky Way. And here's another galaxy, right? All right. And in terms of meters, do you know how large this our universe is in terms of meters? Well, this is about 10 to the 26 meters, all right? All right, so, and if we zoomed in, all right, if we zoomed in about 10 to the 5 meters, all right? So if we zoomed in 10 to the 5 meters, right? How do we zoom in, right? Remember in the last video I talked about Lars? You know, if we go left, we add. If we go right, we subtract, right? So we're going to the right in terms of movement of the decimal places. And now we're at 10 to the 21 meters, all right? 10 to the 21 meters. And now we are looking at our Milky Way, all right? We're just looking at the Milky Way, which means that what we're doing is we are just zooming in on this Milky Way, all right? This is called our galaxy, Milky Way. And in terms of size, this guy is 10 to the 21 meters. All right, so now I just want to look at the Milky Way, and we're going to go into our solar system, all right? So let me draw our Milky Way one more time. So here's our Milky Way, right? This is Milky Way. So let's just say Milky Way. And we labeled this guy about 10 to the 21, right? It's about 10 to the 21 meters. And from there, we zoomed in about another 10 to the 8 meters, right? 10 to the 8 meters. And when we zoomed in 10 to the 8 meters, we got to our solar system. Solar system. And our solar system is about 10 to the 13 meters. All right. So here is our sun, surrounded by all of the planets, right? And that's our solar system. So that's about 10 to the 13 meters. All right. So you're kind of getting an idea of the power of meters and how, changes in, the degree or the magnitude of the amount of meters can change in terms of size, right? We went from our universe to our galaxy, right? Then from our galaxy, we went to our solar system. And now we are going to analyze even further and zoom in one more time, right? Let's zoom in one more time and get to our planet Earth, all right? So let's look at planet Earth. So there's North America, all right, South America, all right? So let's just say this is planet Earth, all right? Earth. All right, and let's say Earth is, and let's just say now we zoomed in about 10 to the 6th meters, all right? And now we are at about 10 to the 7 meters, all right? And now we are, let's just say we are looking at the Earth from, I don't know, our little spaceship, all right? Right? This view is 10 to the 7 meters. Isn't that crazy, huh? That is the power of the metric system. And if we zoom in even more, so let's just say we went from Earth, right? We went from planet Earth, planet Earth, which is 10 to the 7 meters. Right, this is Earth. And we zoomed in an extra 10 to the 9 meters. We would be looking at right? a B. All right, so we went from 10 to the 7th to 10 to the 9th. We zoomed in, right? We went to the right of the decimal 9 places. And now we are looking at this insect right here. Right? Insect. Right? This B. And this B is about 10 to the negative 2 meters. Right? In terms of size. And from there, let's just say we zoomed in another 10 to the 8th. All right? Zoomed in another 10 to the 8 meters. All right? And now we're looking at an atom. All right? We're looking at an atom and its electron shell. Right? We're looking at an atom and its electron shell. And overall, the atom spans across its electron shell about 10 to the negative 10 meters. Right? And this is the atom. Right? So what do we have here? We're looking at the atom maybe through an electron microscope, right? We have we're spanning from the electron shell. We're seeing the nucleus, but we can't zoom in yet, right? We're just looking at the atom, right? And you know when we talk about an atom, what are we talking about? We're talking about any item, right? Any item on the periodic table of elements. So of these, right, some examples, what are some examples, right? We have argon, we have neon, right? We have calcium, we have helium, right? These are all examples of what you will find on the periodic table, right? Not in any order, not in any characteristics of orders, right? But just in general, right? And then let's just say we zoomed in another 10 to the 5 meters, okay? So we zoom in another 10 to the 5 meters, okay? And where are we at? We're actually let me change colors here. All right, that's not working. So we are looking at the nucleus itself, okay? So we have some protons, we have some neutrons, right? Right, let's just say this is what it looks like, right? And in terms of meters, this is a view of 10 to the negative 15 meters, okay? 10 to the negative 15 meters. And that is the nucleus. So that was what I was trying to show you. I was trying to show you the importance of the metric system, and how changes in placement of the meters when we go from kilometers to centimeters or whatnot, right? And even when we go even higher, right, in terms into larger units, we're looking at different levels of length or size, right? So we're looking at the different aspects of length as we travel and we magnify, right? We go from the universe to a galaxy, and then from a galaxy to the solar system, then to planet Earth, then to an insect, right? Then to an atom, and then finally to a nucleus, right? So we're seeing a complete view of the power of the metric system. all right? And just how relative, how important, your, um, lengths are. So before we get any further into our physics lecture, what you guys really need to learn are prefixes, okay? So prefixes are very important, right? Prefixes are very important because it's going to come a lot in terms of conversion, right? Because we're going to be, like I said, we're going to be needing to change from kilometers to meters, kilograms to grams, right? From decimeter, I don't know, maybe you need to go from decimeters to meters, right? Millimeters to meters, right? So we need to know what does milli mean, right? What does kilo mean, right? What does micro mean, right? So we need to know all of these different prefixes so that we can continue on with our lectures, right? Especially when you need to learn about when you're trying to do math calculations and you're confused because you don't know what a prefix means, you need to look it up, right? So I'm just giving you ahead of time some of the prefixes that you might find on your MCAT or on any practice questions when you start studying for your MCAT. And some of these prefixes are deci, okay? Deci, centi, milli, micro, nano, and pico. All right? Deci means 10 to the negative 1. All right? Centi means 10 to the negative 2. Milli means 10 to the negative 3. Micro means 10 to the negative 6. Nano means 10 to the negative 9. And pico means 10 to the negative 12. 10 to the negative 12, all right? And these prefixes will hold still when the ending has grams in it, when it has meters in it. So let's look at an example, right? So maybe it'll kind of help make you understand what I'm trying to get at, all right? So let's just say you have about, let's say you have about 5 grams, okay? And they want you to convert it into decigrams, right? Decigrams. All right? So the way that we're going to do this is, we know, well, let me just go ahead and change this. That 1 gram, all right, let's just, 1 gram is equal to how many decigrams, right? So 10 to the 1 decigrams, right? 10 to the 1 decigrams is equal to 1 gram, right? So if you want to convert, right? Or actually, let's write it the other way. It's actually easier that way, right? We want to convert it. So we have to go 10 to the 1 grams. Ten to the 1 decigrams, right? Decigrams is equal to 1 gram, right? So if you want to convert grams to decigrams, right, you have to cancel out the grams. So grams cancel. All we're left is with decigrams, right? So we are left with 5 times 10 to the 1 decigrams. And that's one way or reason of looking at why you need to know the prefixes. All right, 5 times 10 to the 1 decigrams, or 50 decigrams, right? So let's go ahead and erase this. All right, and let's look at another example that we might need to use. So in our next example, okay, let's just say, I don't know, you have a question and you have to convert, I don't know, you have to convert 10 centimeters into 1 meter, or in terms of meters, right? How many meters is it, right? So, well, first thing we need to know is how much is 1 meter in terms of centimeters, right? 1 meter is centi, right? So 10 to the negative 2, meaning that there's 10 to the second power of centimeters in 1 meter, right? So if we go ahead and convert to meters, all we have to do is multiply by 10 centimeters, right? So 10 divided by 100 is how much? Well, 10 divided by 100 is 0.1. So it's 0.1 meters, right? That is how much 10 centimeters is in terms of meters. All right. So, right, 0.10 meters. Okay, so now let's look at another example, all right? And this is our last example because, like I said, this is supposed to be supplemental, and it's not going to be as good as a review as if you do your own studying, but this is just here to help you out, all right? So let's go ahead and do picogram to, I don't know, microgram, all right? All right, so let's just say okay, so how would I approach this, right? So the very first thing I'll do is I'll go from gram. All right, so I will try to go from gram to picogram. So I would say, okay, so how much is in 1 gram, right? Well, we know 1 gram has 1 times 10 to the negative 1 times 10 to the 12 picograms, right? So 1 gram is equal to 1 times 10 to the negative 12 picograms. Then from there, all right, so actually, so let me just go ahead and erase that. Let's just say we have a certain amount of picograms. Okay, let's just say we have 5 times 10 to the negative 13 picograms, okay? 5 times 10 to the negative 12 picograms, all right? And we need to convert this to micrograms, all right? How would we do this? Well, let's first set that up. 5 times 10 to the negative 12 picograms, right? And then from there, we are going to break this down. We have 1 times 10 to the 12 picograms is in 1 gram, right? So let's go ahead and do that calculation first, all right? 5 divided by 1 is how much? 5 times negative 12, right? Minus 12, right? Is how much? Is going to be 10 to the 0, right? Negative 12 minus negative 12 minus negative and minus 12 is how much? All right? And that's going to be negative 24. Negative 24 grams, right? 5 times 10 to the negative 24 grams. And then we're going to calculate from grams. All right, so let's just go ahead and erase this. Actually, let's go ahead and use another slate. So 5 times 10 to the negative 24 for grams. We're going to go from grams to micrograms, all right? And micrograms is in terms of, what did we say? 10 to the 6th, all right? So we have, so 1 gram is equal to how many micrograms, right? So let's look at this. Micrograms. So in terms of micrograms, you have 1 times 10 to the negative 6, right? So 1 gram has 1 times 10 to the 6th micrograms, all right? So we're going to go ahead and do the same thing here to get into the micrograms, all right? So we're going to multiply 5 times 1, which we said was 5. And we're going to add negative 24, right? And 6, and we're going to get 10 to the negative 18. And that is going to be our answer for micrograms. All right? So, and we cancel out our units. So now you understand why it's very important that we memorize this table right here. Okay? This table right here, right? Because it's very important that we know how to convert in between the different units, in between the units of grams and the different units of meters, right? So that's why I wanted you guys to learn that first, or even look at it, because it's going to be very important when we start getting into Newton's laws and translational motion. So that was why I introduced you to that in the first place. All right, so now that we talked about SI units, let's go ahead and talk about our first lecture in physics. Okay. So our lecture today is going to be about translational motion. Translational motion. And before we actually talk about translational motion, I just want to emphasize some things that my old instructor taught me. All right, so physics is physics sounds hard, and it is hard. But what you need to know is that most of the MCAT, it only tests based off of algebraic physics, and so there's not much calculus based physics. Okay, so there's no calculus. All right. And the second thing I want to say is that I think that that for me the number one thing to solve these problems was to have confidence. Okay, so to have confidence in the physics, whenever you see a physics question, right? In the physics section, okay? All you really need to know is, you have to memorize some equations. Memorize equations, okay? You need to understand concepts. And you need to be confident, all right? These are the 3 things you must do. You must have, all right? All right. So our agenda today we'll cover these topics. All right, and what are these topics? All right, so we are going to be talking about vectors and scalars. we'll be talking about adding vectors, and subtracting vectors. We'll be talking about multiplying vectors. And we'll talk about applications of vectors. All right. And we're going to look at the major kinematic equations and all right. Actually, let me go ahead and take this out. Oh, okay, yeah. So 1 second. So then we'll be talking about the major kinematic equations. And then we're going to look at translational motion. And then we are going to get into projectile motion. Alright, so let's look at vectors and scalars. So A is vectors and scalars. Alright, so usually we use vectors and scalars to describe a motion, okay? Describe motion. And in order to describe motion, we have many terms to describe motion. We have terms like velocity, okay, acceleration, we can, how else could you describe motion? We can talk about speed, right? Right? We can talk about force, right? So these are just a few ways we can describe motion, okay? But and when we usually think about speed, we are talking about velocity, okay? All right? But what is the difference between speed and velocity, okay? All right? So speed can just be 10 meters per second, okay? And that could be speed, right? Because we have a magnitude, right? But velocity is both directional and given a magnitude. So let's go ahead and understand this better, all right? So we're going to go over here and we are going to try and understand the difference between vectors and scalars, all right? So far, we understand that a scalar has magnitude, okay? But a vector has direction and magnitude. Direction and magnitude. All right? So, examples of scalars, right, would be what we are accustomed to, okay? So speed would be a scalar, right? But a vector would be something that has speed and direction, okay? Or magnitude and direction, like velocity, acceleration, and force. All right. So let's look at this. So speed is a scalar and an example of speed is saying 10 meters per second. Velocity is a vector, and an example of velocity would be saying 10 meters per second north, right? 10 meters per second northeast, right? So there is direction to the vector. Now, acceleration is also a vector, right? We can say that an object is accelerating 10 meters per second squared north, right? We can say that it's accelerating 10 meters per second squared northeast, right? And because of that, we have both direction and magnitude. Right? And same here, we have both direction and magnitude. All right. All right. So now that we understand that a vector has both magnitude and direction, let's graphically represent a vector, okay? So when we're adding, we're going to talk about adding and subtracting vectors, okay? All right. So a vector is a force, okay? All right. So a vector has both direction and magnitude. Okay. So let's just say this is vector A. Vector A, and this is head, and this is tail. All right. This is the head of the vector, and this is the tail of the vector, all right? So the vector has direction and magnitude. So let's just say that this is 10 meters per second northeast, east. All right. So let me just redraw this. So we have this vector. There's a head component and there's a tail component. It has a magnitude of 10 meters per second, and it is in the northeast direction, okay? And because of that, we have labeled it a vector. All right? So, let's see how let's see how we can subtract vectors, okay? So in order to, well, first of all, to add vectors, you have to add head to tail. Head to tail. All right? So let's just say we have another vector here. So let me just go ahead and erase this. Head to tail. So here's another vector. And here's so this is vector 1 and this is vector 2. And you want to add this, so here's head and here's tail. All right? And you want to add vector 1 and vector 2, right? So, in order to add the vectors, you must place the tail and head together. All right? And that's how you're going to add. So, in this example, if you were to add these two, and let's just say this is 5 meters per second northeast as well, all right? You would place head to tail, vector 1, and in order to add, you would add head to tail right there. Head to tail. All right? And if this was 10 meters per second and this one was 5 meters per second, your new vector would be 15 meters per second northeast. All right? Is because you have to use the head to tail method. You add the two vectors together and you get the new vector. All right? So let's do a few examples of how that's going to look, all right? So let's go ahead and look at a few more examples. You have another example where you're supposed to add this vector 1, and vector 2. All right. In order to add these two, so if you were to add these two, you would have to do head to tail method, right? Here's the head and here's the tail. Here's the head and here's the tail, right? So you put head to tail together. And your resulting vector is going to be vector 3. All right? So same thing. Let's look at this one. So say you have another vector This vector looks something like this. Head to tail. Head to tail. And this vector, this new vector is going to also be using the same method, right? So we took vector 1, head to tail, and we summed with vector 2. Head to tail. And this will be our new vector, right? So our new vector, right? Alright. So now we kind of understand how adding of vectors is done. So now how about if you were to subtract vectors, okay? Subtract vectors, okay? So if you were to subtract, let's just say you had vector A minus vector B, all right? And you were trying to find this new vector, okay? So you had vector A, let's just say this is vector A, and you have vector B, and you have to subtract vector B, right? You're not adding vector B, so you have to subtract vector B. All right. So you have two possibilities. One, what you can do is you can use the head to tail method, right? And add. And the way you would do that is you would add vector A plus the negative of vector B, right? And what would be the negative of vector B, right? The negative of vector B would be negative of vector B would be the opposite. Okay? So that would be negative vector B. So if you were to add this, we could do the head to tail method, right? So let's see, head. So the head to tail. And let's just say you're trying to do that way, right? Right? And what you would find out is that if you put this head at this tail, the vector would cancel out, right? And the difference, actually, let me just go ahead and let me just erase this. The difference on whichever one is bigger will result in a new vector. That'll be the vector, the vector in question, okay? So that's one way you could do it. The next way we can do this is to subtract the vectors, okay? So you have, and it's called, it's a new way, it's called, you have to put both the heads together. So when subtracting vectors, you have to, when you're subtracting vectors, you have to put both heads together. Put both heads together. And draw a tail, a long line along both tails, okay? And draw draw a tail along. So let's look at this. So VA minus all right, so let's go ahead and look at an example. Okay, so we are adding VA and VB. Okay, so VA looks like this and VB looks something like this. Okay, so in order to subtract VA and VB, first you have to put the two heads together, right? So what is it going to look like? So this is VB and this is VA. All right, and the product is going to be the subtraction of both of these vectors, this new vector. All right, so let's look at another example. All right, so let's go ahead and do another example. All right, you have one vector like this, VA, and you have another vector like this, and you want to do VA minus VB again, right? So let's put both of the heads together again. And we're going to draw the vector again. And that's going to be the new vector. That's it. Alright, so now let's go ahead and look at another topic, and that is going to be multiplying vectors, okay? Multiplying vectors, okay? So for the MCAT, the only thing you really need to know is that you don't necessarily need to know how to multiply to multiply two vectors together. The only thing that you really need to know is the effect that's going to happen is if you multiply a scalar by a vector, right? So if you have a vector, I don't know, 3 newtons, right? 3 newtons northeast, right? And you multiply that by a scalar of 3, well, what's going to happen, right? The only effect is that instead of it being 3, it's going to be 9 now, right? So it's going to be 9 newtons. 9 newtons northeast. That's the only difference that multiplying a scalar by a vector is going to have. So that is pretty much the only thing you need to know about multiplying vectors, right? So you don't need to know anything about dot products or cross products. All right. So the next thing that we're going to talk about is finding vector components, all right? Finding vector components. And besides finding the difference, besides knowing the difference between vectors and scalars, I think the second most important thing that you need to know, well, probably the most important thing out of this lecture, is to know the components of the vector, right? So if you have this vector A, you need to be able to understand its components, right? So it's going to have an x component, and it's going to have a y component, right? And you need to know how, if given an angle here, how to get that opposite angle, right? So, or that opposite value, right? So that's where SOHCAHTOA comes into place, right? Sine is a sine of an angle is equal to opposite over hypotenuse, right? Cosine of an angle is adjacent over hypotenuse, right? Tangent is opposite over adjacent, right? So let me just go ahead and write this, right? Like sine of theta is equal to opposite over hypotenuse, right? Cosine of theta is equal to adjacent over hypotenuse. Tangent of theta is equal to opposite over adjacent, right? If there's a better way, if you just kind of want to memorize, right, you can break down vectors into the both components, right? The x component and the y component with this. So another way of looking at this, right, is that if this vector had a value of v, this x value would equal v times the cosine of this theta. And this y would be the vector times sine theta. And these would be both ways of getting the component vectors. So why are these important? Because we will need this when we're talking about projectile motion, and we get into Newton's laws. And one thing to keep in mind is that all vector components will form right angles when put together. So here's a right angle, right? So if the vector looked like this, right? Let me show it on the next one. So if the vector looked like this is vector A. Well, there's a component going this way and a component going this way, right? So right angle is formed, right? So this is the x1, right? So v times cosine of theta. And you have a y-axis, right? V sine theta. So let's give another example. You have, let's say you have a downward force. So we have vector b, right? So it's going to have a downward component, and it's going to have a sideways component, right? And this is the y. This is the y-axis. So this would be v sine theta. This would be your theta, and this would be the x-axis, right? So here is that right angle again, right? So yes. So let me go ahead and draw one more. So what would be the case? Force was like that. Force was like this, slightly more elevated, okay, something like this. Okay, right, so you have force like, you have one like that, right? Angle, theta, right? This is v sine theta, v cosine theta, right? All right, so now let's look at some applications of vectors and scalars. All right, so let's look at some scalars, okay? Scalars would be distance and speed, right? Speed is calculated, right, by distance over time. All right, so let's just look at some formulas, okay? Speed is distance over time, right? Now let's look at some vectors. All right, and the vectors that we have are velocity and displacement. All right, and velocity is considered displacement over time. Now we're going to look at some examples to compare the difference between speed and velocity. So in order to understand the difference between velocity and speed, what you need to do is understand the difference between displacement and distance. All right, and so what is the difference? So if you were driving in a car, right, and you want to go from point A to point B, all right? Point A to point B, right? The net distance, okay, or the net difference between the distance, the net difference between the two destinations is called displacement. All right? So from point A to point B, the difference between point B minus point A is your displacement. All right? But if you took the same car and you went from point A and you were going to point B, but in order to get to point B, you went a longer route, right? And you took, let's just say you got off the route and you took a couple of detours, and because of that, the actual trip should have taken you about 50 kilometers, right? But because of your detours, it took you about 150 kilometers, right? The difference, or this 150 kilometers, right, will be considered the distance you traveled. All right? But the net distance between point B and point A is referred to as displacement. All right? And it's the result of taking point B and subtracting point A. So to sum up, displacement. So when we talk about displacement, okay, displacement is considered relative to a starting point, right? So it's relative. It's relative to a starting and ending point. Okay. So these are the only two factors considered in displacement. So if you go from point A to point B, that is the only thing that matters when considering displacement, okay? It doesn't matter if he actually went from here to here to here to here, right? It doesn't matter if he actually went from, it actually took him from here, it took him this much, right? The difference between point B and point A, right? This value right here is considered the displacement, right? Everything else, right? The red and blue is considered distance. All right. So when we look at the difference between velocity, right? So velocity, we describe velocity as displacement over time. And we considered speed distance over time. What this is saying is that you can have, right? You can have different values. You can have different values based on the route that was taken to what was the net value of position A and position B. All right. All right. So now let's look at acceleration. Okay. So we know acceleration is also a vector. So acceleration is also a vector. All right. And acceleration formula. That formula for acceleration is equal to the change in velocity over time. Okay. Change in velocity over time. So what that means is v final minus v initial over time is equal to acceleration. So now we understand that acceleration and vector or acceleration and velocity are both vectors, right? But one point that I want to make is that, so let's just write out acceleration. So acceleration is the change in velocity over time, right? And since it's a vector, right, only the net velocity matters, right? So the final velocity upon the ending of the time, and the initial velocity of the beginning of the time over the amount of time that was traveled, right, is the acceleration, right? So in order to for you guys to understand the point that I'm going to make, is I'm going to give an example. All right, this example is going to look like this. So we have two cars, all right, or we have one car, and his initial velocity, v initial, is going to be 75 miles per hour. Or let's just do miles per hour, right? Because that's what we know most. And I guess you guys haven't learned the metric system or looked at the metric system yet, because we just introduced it. So we'll start off with this. All right. So V final is, let's just say, 90 miles per hour. All right. So if we were to look at acceleration, in order to find acceleration, what we would do is we would subtract V final, and let's just say this, it went from 75, let's see, we'll say in time, in 1 hour, all right? Right? And we did the math, right? So we did 90 mh minus 75 mh, right? Over, it took 1 hour, right? And what we got is, we got acceleration, right? What's 90 minus 75 is 15, right? So we got miles per hour squared, all right? And it's a vector, so it's positive, right? Because difference is positive. So in this case, right, we have positive acceleration followed by a positive change in velocity, right? right? Because velocity is increasing, and a good amount of distance has been traveled, right? Because of that, we have both positive acceleration and positive velocity. So now let's look at the next example, all right? Once again, acceleration is equal to change in velocity over time, right? And let's just say we have the same car situation, but the speeds are just slightly different, right? All right. And the V initial for this car, this guy, is 75 miles per hour. And V final for this guy is 55 miles per hour, right? So over this time of 1 hour, all right, he has decreased his speed. All right, so let's go ahead and look at acceleration. Acceleration is V final minus V initial over time. Took him 1 hour. So V final is 55 minus 75, right? We got to make sure that we have our units, right? Because units are very important, and it's going to help us cancel out answer choices that are wrong, right? Miles per hour minus 75 miles per hour, right? And we're going to divide by 1 hour. And what's going to happen is we are going to get a negative 20 miles per hour squared acceleration. All right. So we in this situation, what has happened is our velocity has a positive value, right? Or positive vector value, right? While our acceleration has a negative vector value. You see that? So the point that's being made is that just because speed or just because you normally associate speed with acceleration, that is not always the case. You can have a positive velocity, and you can have a negative acceleration, or you can have a positive velocity and also a positive acceleration. Let me just go ahead and put that positive there. All right. So the next topic we're going to talk about is the major kinematic equations. The major kinematic equations. All right. So far, we have introduced the values of all those kinematic equations, right? We talked about displacement, we talked about velocity, right? We talked about acceleration, right? We talked about time. And now what we're going to do is we're going to take all of these variables and we're going to make equations to help solve translational motion problems. Translational motion problems. All right. And when we talk about translational motion, all right, I usually think of, when you translating, right, from going from point A to point B, right? Thinking about, a person walking from point A to point B, or a car traveling from point A to point B. So point A to point B. That's translational motion, okay? And that's the type of question those are the type of questions that you're going to see in any translational motion problem, all right? So the major translational motion problems that are equations that you're going to have to memorize for the MCAT are these equations right here. So one is over displacement. Displacement is equal to x is equal to x initial plus v initial times t plus 1/2 at squared. All right. The second equation that you're going to need to know is that v final is equal to v initial plus at. The third equation that you're going to need to solve or understand is this: v final squared is equal to v initial squared plus 2 acceleration times distance. And the fourth is just going to be v instantaneous, right? It's just going to be v final plus v initial divided by 2. And now these equations can solve any translational problem, and it can also solve any projectile problem on the MCAT, okay? On the MCAT. Okay? So, how do you solve translational problems? Well, what you do is you first write out all variables given to you by the question, okay? So usually they'll give you 4 out of 5 variables for the question. All right? And based off of those variables, you'll be able to plug and solve to find the missing variable. All right. The second thing you need to do is you need to draw out a picture, right? Because it's going to help you better understand what's actually happening in the problem. So translational problem is about moving one object from one point to the next point, right? If you draw a picture like I drew over here, right, it's easier for you to solve those problems, right? So drawing a picture always helps. All right, so let's look at a few examples then. All right. All right, and before I move on to a problem, I actually just want to show you a quick way that I make sure or double check these equations. All right, so let's go ahead and move on to, let's rewrite those equations, okay? And I'm going to show you how I double check and make sure that I know all the equations, okay? So one, we have x is equal to x naught plus v naught t plus 1/2 at squared, right? And the way I do this is by looking at the units, all right? So distance is measured in meters. So we know that the answer has to also be in meters, right? So let's go ahead and look at these dimensions, okay? So our first answer is in meters, right? Second answer is velocity, which is usually meters per second times seconds, right? And you have 1/2 meters per second squared times second squared, right? And, you know, if you ever write out the equation on the test or a practice problem, you can always just look to see if the meters equal each other, right? Velocity times time is going to cancel, and you're going to have meters here. Acceleration times time squared, you're going to cancel, and you're going to have meters equal to meters, right? So it worked out, right? So that first equation you wrote right, all right? So now let's go ahead and look at the second equation, all right? Let's look at this second equation, all right? This second equation is V final is equal to V initial times AT, right? So let's look at meters per second is equal to meters per second plus meters per second squared times time, right? So you gotta cancel, right? We're still left with one S. So meters per second is equal to meters per second, right? Plus meters per second. So we know we wrote this equation right? So we can go ahead and erase this too. And so I'm just gonna go ahead and do it for the other ones just to show you that all the all the units work out. Right? Meters per second squared is equal to meters per second squared plus 2 acceleration, right? Which is what? Meters per second squared times distance. And what we got is what? Times meters. Yeah, so okay, let's look at this. What did we do wrong here? So we have done something wrong here. So meters per second squared, meters per second squared, right? So this is a good example. We realized that our meters, our units do not cancel each other out now, right? Why? Because right here, we let's use a different color. We realized that acceleration, we used the velocity formula for acceleration, and we also squared it. Did you see that? So that's where we messed up. So does the units add up? So does meters cubed over s squared equal to meters squared over s squared? No, right? So that's how you know we did something wrong. So this third equation, we did something wrong. So let's go ahead and correct that. Let's go ahead and change this right here. Let's go ahead and change this. What we have to change is we have to change this right here. We have to change this right here. What is the units for acceleration? It's meters over seconds squared, right? Meters over seconds squared. So now, does meters squared over s squared equal meters squared over s squared? Yes. So now this equation has become valid. So now we're going to go ahead and erase this again. So now let's go ahead and look at our last equation. So our last equation looks something like this. Okay. And our last equation is going to be V instantaneous is equal to 1/2 V initial plus V final, right? And velocity is equal to the average of velocity, right? So that one was pretty straightforward. So let's go ahead and erase that. Let's go ahead and erase that. And now let's go ahead and look at this equation, okay? Or this practice problem. A driver is moving. Let me go ahead and change this. A driver moving at a constant speed of 10 meters per second sees an accident up ahead and hits the brakes. Okay, so a driver is moving fast, and all of a sudden, and he's going 10 meters per second, and all of a sudden he sees something and he decides to hit the brake, right? Pop, he hit the brake, right? Maybe he saw a stop sign or something, all right? If the car decelerates at a constant rate of -5 meters per second squared, how far does the car go before it comes to a stop? All right, so let's write down all the variables we have here, right? So like we said, so we have a constant speed of 10 meters per second. So his initial velocity was 10 meters per second, right? And he sees an accident up ahead and hits the brakes. Okay, so now he is decelerating at a constant rate of -5 meters per second. So his acceleration, right, is -5 meters per second squared. Remember, we said that the velocity vector and the acceleration vector don't have to be in same direction, right? So let's go back. If the car decelerates at a constant rate of -5 meters per second squared, how far does the car go before it comes to a stop? All right. So he has come to a stop, right? So they're saying here, how far does the car go before it comes to a stop? So we could assume that it has come to a stop. So V final is 0 meters per second. Okay. And what do we want to find? What does he want to find? He wants to find how far does the car goes, right? So they want us to find the distance, right? So, I mean, you can either write down all of these variables, like I said, or what you can do is you can draw the picture, right? This is translational motion. This is a good example of a translational motion equation, right? So all of a sudden, this guy is driving, and he sees a stop sign, right? Stop. And he decides to stop, right? Initially, this guy right here was going 10 meters per second, right? Sorry, I meant to say meters. If I said miles, I'm sorry. And his V final is equal to 0 meters per second. And what we're looking for is the distance that he's traveled from here to that stop sign, right? What is D? And while this guy, right, here's this guy, and he saw the stop sign, he decided to decelerate. So he's decelerating here, right? So we have a vector in the opposite direction, right? And because of that, he is decelerating, right? He's decelerating by how much? -5 meters per second squared. So this is kind of the scenario. So drawing it actually makes everything easier. So now we know that what we're trying to find out is the distance from the moment he's noticed that stop sign, and how far he had gone till he had hit that the 0 meters per second, right? Or 0 meters per second. So we can, if we know our equations and we know that we're trying to look for the value D, right? We're looking for D. 1 second. D. Let's go ahead and look and see which equation is best for this. So we have, what variables do we have? We have V final, we have V initial, we have acceleration, but we don't have distance. So now let's use this equation to solve this problem. And it can be just as simple as that. So if you have memorized those equations, it can be as simple as 30 to 45 seconds. So let's just plug and chug and find out what that answer is, right? So V final squared is equal to V initial squared plus 2 acceleration times D, right? Let's go ahead and see if let's just say we memorized it and we want to see if our equation is right. So let's go ahead and check the units. Meters per second squared times meters. So meters squared over s squared is equal to meters squared over s squared plus 2 times meters squared over s squared. Okay, so the units work out. Okay, so our equation is right. All right. So our equation is right. So now let's go ahead and plug in all the values, okay, that we have. So let's go ahead and plug in all the values. V final is 0. So 0 squared is equal to, what is V initial? V initial is 10 squared, right? And we have an acceleration that is negative, right? So negative 5 plus d, right? And we're looking for d. What is d? So we are going to solve real quick, right? We're going to get negative 100. Negative 100 meters per second is equal to negative 10 meters per second squared, right? Times d. Once we divide these two, we end up getting 10 meters as the distance. So this distance right here, this distance right here is 10 meters. So it took him 10 meters to realize the stop sign and stop. All right? And that's how simple solving these problems can be. All right. Now the next thing that I want to go by you guys is understanding velocity versus time graphs and displacement versus time graphs. Okay. So first thing, let's look at a displacement versus time graph. Displacement versus time graph. All right. So here is displacement. Let's just say this is called displacement versus time. All right. So the very first thing that you need to know is that, right, displacement is a vector. All right. And so at any moment, your displacement can change, right? Depending on what your starting point is and what your ending point is, right? The second thing that you need to know is that the slope of the graph, right? The slope at any point. So the slope at any point. So let me go ahead and draw this in. Here's a point. Here's a point, and here's a point. The slope at this point, and the slope at this point, and the slope at this point are representative of what we call the instantaneous velocity. Right? Next thing you need to know is that the area under the curve means nothing. All right. So this area right here means nothing. All right. And so another way of looking at this is, another way of looking at this let me go ahead and erase this, is that the slope also points to the direction of the velocity. All right, so let's look at another example. Here we have change of x and t, right? So let's just say this is our new graph, right? What this is showing is that at this point, velocity is positive, the slope is negative here, velocity is 0 here, steady, velocity is positive, right? Velocity is positive, and velocity is positive. That is what that's showing. So the slope also points to the direction of velocity. The slope also points to the direction of velocity. So now let's go ahead and look at another graph. This one is going to be our change in velocity over change in time graph, okay? So when we look at that graph, all right, let's go ahead and look at that graph, okay? So let's just say we have another graph that looks something like this, all right? All right. And this change in velocity graph also shows similar results, right? Here, the number one thing you should know is that the area under this graph has meaning. Okay? The area under this graph represents the distance. Distance. All right? And also, so all of this represents distance. The way you solve, right, will be like that. You are going to, what are you going to do? You're going to find the area here. You're going to find the area here, find the area here, find the area here, and you add all those up, and you would get the distance. You're going to get the distance. And similarly, by looking at the slope, right, you could see that there was a negative acceleration here, right? Acceleration is change of v over t. So here is negative, here is 0, here is positive, and here is neutral, right? So that's another point that you need to look at. So you need to look at the slope. You need to look at the slope of look at slope to understand acceleration, right? Now you can also, So these are the only major things that you need to understand from a velocity over time graph. Okay, so you understand slope is representative of acceleration. You know the area under the curve is representative of the distance, right? But here's actually a complication of the velocity versus time graph. Okay, that we need to know. So we have time here, and we have the change in velocity, right? So here's the complication. So you go down, and then all of a sudden you have a drop here, and it drops off this way. Okay, so let's just kind of draw this out like this time. All right, so we can look at displacement and distance. All right, distance will be equal to the sum of all areas under the curve. And it is the sum of the absolute value of all areas under the curve, right? Which means that this will be considered distance. This would be considered distance, right? But this would be considered a positive distance. And this would also be considered distance, right? Now, if you used displacement, right? If you were measuring displacement, what you would have to do is, if this was, this is actually a better idea. So if this was area 1, this was area 2, and this was area 3. For distance, you would say distance is A1 plus A2 plus the absolute value of A3. And that would be distance. Okay, displacement is equal to A1 plus A2 minus A3. That is displacement. So you would subtract this value. Instead. All right. So our final topic for today is projectile motion. All right. Projectile motion. And the importance of projectile motion is that it is not the importance, but the complication of projectile motion is only that projectile motion deals with two components, right? Remember we talked about the x and y components of a vector, right? It talks about the x and y components. So let's go ahead and look at these x and y components, all right? And it requires a little bit more critical thinking, but once if you draw the picture, and understand, if you draw the picture and understand the equations, the kinematic equations, you're gonna do fine. So how do you know when you have a projectile motion equation? Okay, so an example of projectile motion would be like like someone shooting a cannon. Cannon is shooting, okay? Or you know, a ball is thrown in the air. In the air, right? A ball is thrown in the air. An object is dropped, right? For me, usually the first step in understanding a projectile motion problem is always to read the question and draw a picture. All right. And usually, most projectile motion problems can be solved by just drawing this arch. All right. And depending on how you understand this drawing will dictate if you understand projectile motion. All right. So let's look at an example we have here. Okay. So let me draw it better on this problem here. So we have a projectile motion. Let's draw a cannon here. So this is our cannon, all right? And let's just say that, we have a ball that, like a cannonball, that is shooted out of our cannon, all right? All right. And let's say that this vector is about 10 meters per second. 10 meters per second, okay? So they shot this ball. It doesn't have to be a cannon, whatever it is. It's shot out at 10 meters per second, okay? Now there's two components too. Remember we talked about the x and y component, right? And the degrees. If they give us the degrees, then we need to break it down and solve what that is. But usually what I do is I break it into the x component and the y component. Remember when we drew this, what did we do? We showed you the different components, right? So here was the 10 meters per second, and here was the x component, the 10 cosine theta, and here was the 10 sine theta, right? So we have two sides to this equation, right? Few things that you need to remember is that at the very tip, at the maximum height, at max height, all right, there is what do you call there's complete loss of y component, all right? So the y component no longer exists at the peak, which means that if you want to solve for height here, you can solve for height, all right? You can solve for height by using the height component formula, right? But remember, even when we're solving projectile motion, we have to make sure that all equations are in line with the components plugged into the equation. Plugged into the equation. All right, so let's kind of understand what I'm trying to say here. So I'm gonna erase this. All right. So let's go ahead and erase all this right here. All right. So this y component. So we can find the height, which is the max height, using this equation here. V final squared of the y component is equal to V initial squared of the y component plus 2 acceleration times the distance, y, right? Because this is the maximum height, which this is a distance, right? Distance of y. We need to make sure that all of these are in terms of y. And that's what we're doing. So, based off of this equation, if we assume that this theta is equal to 30 degrees, okay, then what we can do is we can plug in V initial. We know V final, right? We know V final is 0 here, right? There is none there. So 0 squared is equal to 10 sine of 30, and we can square this, and we can take 2 and multiply by acceleration, right? Any object that is in the air will always experience acceleration downwards, right? Because of gravity. So acceleration is 10 meters per second squared. So 2 times acceleration is going to be 10 times the variable that we're solving for, right? So what is 10 sine 30? Well, let's go ahead and look at this. Let's look at the sign. Remember, I showed you the easy way of solving that first quadrant. So let's look at this. X is on the x-axis, so this is 1, 0. Y, 0, 1. Since it's going from 1 to 0, we're decreasing, right? So square root of 3 over 2, square root of 2 over 2, 1 over 2, 1 half, square root of 2 over 2, square root of 3. So 30, 45, 60, and 90. Alright, so now let's look at this. So 10 sine 30. So the sine of 30 is 1 half. So we have 10 times 1 half squared. So that's 5 squared. 10 times 1 half is 5 squared, 25. So that's 25 plus 20d. So 20 dy, right? Because we're talking about the y component. Y component, and we know that this is 0. All right, and since we are talking about acceleration, we know it's negative because we assume that this was the negative position and that this was the positive position. So this is actually a subtraction. So now what we're going to do is we're going to move 25 to the other side, divide by 20, and we're going to get dy, which is the height, the max height. And 25 divided by 20 is about what? It's about 1 point, that's about 1 point, maybe about 1.2 or so dy. So let's just say that's in meters. So this height dy would be about 1.2. And that's how you would solve that. All right, and that's how you're going to find the max height, right? So that is one example of solving for a kinematic projectile motion problem. All right, so let's look at one more example, okay? So in this example, a boy throws a rock horizontally off a cliff. Okay, so he throws a cliff that is 30 meters above the water. 30 meters above the water. Okay? If the speed of the rock is 20 meters per second, how long does it take for the rock to hit the ground? All right. So let's analyze this question. So a few things that we know, right? So the very first thing is let's draw a picture, right? So a boy throws a rock horizontally off a cliff that is 30 meters above the water. Okay, so he is. So let's just say there's this boy, right, and guy is standing here, decides to throw this rock, right, and he let's kind of draw this way, and he throws this off a cliff, and it falls into the water, right? And we know that the cliff that is 30 meters above the water. So let's label that, right? So dy is equal to 30 meters, right? Right. This portion right here is 30 meters. What else do we know? We know that the speed of the rock is 20 meters per second, right? Here, speed is a vector, but speed is a scalar, but we need to, in order to solve this question, let's just assume that they said vector, right? Actually, let me go ahead. If the velocity, let's just put velocity of the rock, okay? The velocity of the rock is 20 meters per second, okay? And we know that the velocity of the rock, v initial, is 20 meters per second, right? How long does it take for the rock to hit the ground, right? So now the question is not about the distance, but it's about the time that it's going to take for that ball or that rock to hit the ocean, right? So v initial is 20 meters per second, we know. V final is equal to what? Once it hits the water, it's going to have 0 meters per second, right? So 0 speed. We know that the acceleration, right, is always going to be downward, right, because of gravity. So acceleration is what? Negative 10 meters per second squared, right? Because acceleration is what? Acceleration is a vector, right? And what are we looking for? We're looking for t. right? Do we know any equations that will help us solve this equation right here? Remember, you're always going to have extraneous information like this, like the height of the cliff, right? But do we need it? Do we necessarily need it to solve it, right? And even then, right? This is a y component question, and we know that the velocity of the rock, we don't know, if it was thrown sideways or if you throw it down. So it's better to analyze the situation before using different variables. So let's go ahead and solve this question, right? We know this equation, right? V final is equal to V initial plus acceleration times time, right? So what is our V initial? Our V initial is 20. Where's V final? 0. Then we have acceleration, -10, and time, what we're trying to solve, right? So let's go ahead and solve this. We plug in our equation and we solve for t, right? -20 is equal to, let me go ahead and erase this. -20 is equal to -10 times t. So t is equal to 2 seconds. See that? And that's how simple these questions can be as soon as you start understanding what's going on. So that's it for today, guys. We went over a lot of things today. Remember that this is supplemental, right? This is supplemental and should not be used as a primary study source. If you guys enjoyed this video, please give a thumbs up, right? Thumbs up. That's my picture of a thumbs up. Yeah, so let me just write that down because that sucks. Okay, thumbs up. Thumbs up. And in the next video, I'll be continuing physics, and we'll be talking about force and Newton's laws. All right, guys. Good luck with your studies, all right? Thanks. Bye.